It's past midnight in interior Alaska. Outside, it is minus 45 degrees Celsius, cold enough that a cup of boiling water thrown into the air freezes before it hits the ground. Bare skin exposed to this air begins to freeze in under 2 minutes. And through this frozen darkness, a 3,000-ton freight train is moving. Inside the cab, one man watches the track ahead. He has been awake for 9 hours. Here is something strange. To slow this train down, that man will not press harder on anything. He will let go. He will release air, let it hiss out into the cold, and the train will begin to stop itself. It sounds backwards. And at minus 45, that one fact, releasing instead of pressing, is the difference between stopping safely and a catastrophe you cannot walk away from. So how does releasing air stop 3,000 tons of steel? What happens to that air when it's this cold? How does a diesel engine even start when the fuel is thick as syrup? And why is there always a second person in that cab, staring at the same dark track? Let's spend one night inside this machine, hour by hour, and find out. Before we climb into the cab, if you like the hidden engineering behind the machines that quietly move our world, take a second and subscribe. It genuinely helps this channel keep going. Now, let's go back to the beginning of the night. 4 p.m. Pre-departure. The cold is already winning. The shift begins before the sun is fully gone, which in an Alaskan winter means it began in the dark. The engineer walks the length of the locomotive with a flashlight, and he is not admiring it. He is hunting for the first signs of failure. Because here's the thing almost nobody thinks about. At minus 45, the enemy is not the cold biting at human skin. The cold doesn't attack people first. It attacks systems. Rubber seals that were flexible yesterday turn brittle and crack. Steel contracts so much that gaps open where there were none. On the rails themselves, you could drop a coin into cracks that appear overnight. Grease thickens into a paste that no longer lubricates. Diesel fuel, normally thin and quick, turns cloudy and waxy as its molecules start to crystallize. This is called gelling, and a gelled fuel line is a dead engine, so the locomotive was never shut off. That's the first counterintuitive rule of the far north. You would think that to save fuel and wear, you'd switch the engine off when it's parked. Down here, it's the opposite. These diesels are often left idling for the entire winter. Days, weeks, sometimes months without stopping. Because starting a frozen diesel at minus 45 is far more dangerous to the engine than simply letting it run. Cold, thick oil won't circulate. Metal parts that contracted overnight don't fit the way they were machined to fit. A cold start can crack a block, so the engine breathes all winter, and the low rumble you hear in an Alaskan rail yard in January is the sound of machines that are never allowed to sleep. The engineer checks the fuel, treated with anti-gel additives that lower the temperature at which the diesel starts to wax up. He checks the air compressor, because tonight, air is everything, and a compressor that can't keep up is a train that can't brake. He checks the batteries, which can lose 40% or more of their cranking power in cold this deep. A battery that turns over an engine easily at room temperature can barely find the strength to at minus 45. He runs his gloved hand along the air hoses between the cars, feeling for the stiffness that means the rubber is one hard knock away from cracking. And he watches for one specific enemy that lives in the air system itself: water. Compressed air always carries moisture, and moisture at these temperatures doesn't drip. It freezes into ice crystals inside valves and lines that are supposed to move freely. So the air dryers get checked, the reservoirs get drained, and it is done carefully, because a single frozen valve deep in the train can hide for hours and then reveal itself at the worst possible second. Everything on this machine that seemed simple in summer has become fragile. A door that closes easily now has to be forced. A latch that snapped shut now has to be coaxed. Grease that flowed now sits like cold butter. This is the real work of the far north. Not driving the train, but keeping the machine alive long enough to. By the time the engineer climbs into the cab, he has already fought the cold for an hour, and the train hasn't moved a meter. 7 p.m. Departure. Why letting go stops a train. The train pulls out into full dark, 3,000 tons stretched out behind the locomotive, rolling on thin steel wheels over thin steel rail. And now we come back to that strange fact from the very start of the night. To brake this train, the engineer releases air. Here's why. The brakes on every car of this train are not held on by pressure. They are held off by it. Running the entire length of the train is a pipe called the brake line, kept full of compressed air. As long as that air pressure is high, the brakes on all those cars are pushed open, and the wheels roll free. To brake, the engineer releases some of that air. Pressure drops, and on every single car, a valve senses the drop and clamps the brakes down. Why build it backwards like that? Because it's a failsafe, and the failsafe is the entire point. Imagine a hose bursts somewhere in the middle of the train. Air escapes. Pressure drops, not because the engineer wanted it to, but because something broke, and the train brakes automatically, all by itself, on every car at once. The system does not trust the driver to react. It trusts physics. Lose air for any reason, and the train stops. In a place where a broken coupling in the dark could otherwise send unbraked cars rolling free. That design isn't clever, it's survival. But at -45, that same air system becomes the thing you fear most. Because compressed air always carries a little moisture. And in this cold, that moisture doesn't just condense, it freezes. Ice forms inside the very brake lines that are supposed to save the train. A frozen valve is a brake that won't release, or worse, one that won't apply. So the air is dried, and dried again. And the engineer watches his air pressure gauges the way a diver watches his oxygen. Down here, the safety system and the biggest threat are the same system. That's the paradox he drives with all night. And there's a second strange thing about simply getting underway. You would think the engineer opens the throttle and the whole train moves at once. It doesn't. Between every car there's a coupler with a little bit of slack. A few centimeters of play, multiplied across 100 cars into several meters of give. So when the locomotive starts to pull, it doesn't drag 3,000 tons all at once. It stretches the train out one coupler at a time, car by car, and you can feel the pull travel down the length of it like a wave. Do it too fast in the cold, when the steel is brittle and the grease is stiff, and you can snap a coupler clean. A break-in too that leaves half your train sitting dead on the track behind you. So the start is gentle, patient, deliberate. Even beginning to move is a skill out here. 10 p.m. The first challenge. A train that can't stop quickly. 3 hours in, a signal in the distance. The engineer begins slowing down. And here you meet a truth about trains that feels almost unbelievable the first time you hear it. A freight train this heavy, moving at speed, can take up to 2 kilometers to stop. Over a mile. If a truck stalled on a crossing and you could see it the instant your headlight touched it, you still could not stop in time. Why? 2 numbers, and both are about smallness. First, the contact. Each steel wheel touches the steel rail on a patch roughly the size of a coin. The entire 3,000-ton weight of this train is riding on a handful of contact points, each no bigger than the tip of your thumb. Steel on steel gives you almost no friction, which is exactly why trains are so efficient to move, and exactly why they are so hard to stop. The very thing that lets one locomotive pull thousands of tons is the thing that makes those tons impossible to halt in a hurry. Second, the weight itself. 3,000 tons is the mass of roughly 1,500 cars, all linked together, all wanting to keep moving. Momentum like that doesn't care about your brakes. And the cold makes it worse in a way you'd never guess. A cold brake system responds slower. The air takes fractions of a second longer to move through stiff, frigid lines. Multiply those fractions across a train more than a kilometer long, and the delay between deciding to stop and actually slowing down stretches out even further. So the engineer does not stop this train. He anticipates it. He reads the track 2 kilometers ahead in his mind, and he begins braking for a problem long before a normal driver would even see it. He knows the grades of this line by heart, where it climbs, where it drops, where gravity will try to run the train faster than he wants. On a downgrade, he starts braking early, feeding it in gently, because if he waits until he needs the brakes, he has already waited too long. Braking here isn't a reflex, it's a prediction. And at -45, with ice lurking in the brake lines, every prediction has to be made early, and made right the first time. There is no second attempt at stopping 3,000 tons. 1 a.m., the real danger, the enemy you can't see. Deep in the night now, and this is where it gets serious. Because the real danger tonight was never the number on the thermometer. You'd assume the enemy is the cold attacking the man in the cab. It isn't. The man is warm. The cab is heated. The enemy is the cold attacking the invisible things, and the most dangerous of those is the track itself. Remember how steel contracts in extreme cold? The rails do it too. In summer heat, rails expand and can even buckle. In deep winter, they shrink, they grow brittle, and under the pounding of a heavy train they can crack clean through. It's called a broken rail, and it is one of the quiet nightmares of northern railroading. A hairline fracture, invisible in the dark under a layer of frost, right in the path of 3,000 tons. This is why the train has systems the engineer never sees working. The track circuits, low electrical currents running through the rails, can detect a break because a cracked rail interrupts the current and trips a signal to red before the train ever arrives. The engineer trusts these the way you trust the ground under your feet, completely and without thinking, until the one night it matters. The far north is full of machines like this, guarding against dangers that never announce themselves. The cold doesn't come at you with a warning. It works in the dark, on the things you can't inspect from a moving cab, and the entire system is built to catch the failure before you feel it. 2:30 a.m., the handbrake in the dark, when the cold finally bites. And then, on a grade, the thing they've been guarding against all night nearly happens. The air gauge flickers. The brakes drag when they shouldn't, or release slower than they should. A hint that somewhere back in the dark, ice is forming inside a valve. On a train that needs 2 kilometers to stop, a brake system that's even slightly unsure of itself is not a small problem. It's the whole game. Here's where the human being earns the night. Because the answer can't come from the cab. Someone has to go out. Someone has to open the door, step down from the warm orange light into air that will freeze exposed skin in under 2 minutes, and walk the length of frozen cars with a flashlight, looking for the valve that's misbehaving. On some cars there are handbrakes, mechanical wheels you crank by hand, the last line of defense when air can't be trusted, and cranking one at -45, with the steel so cold it burns through a glove, is a task that turns a few minutes of work into a fight. This is the moment that explains everything about the far north. The machine is brilliant. The fail-safes are elegant. But when the cold finally slips past all of them, it comes down to a person standing alone in the dark, doing something physical and slow and painful, while the warmth of the cab glows a few cars away like a promise. The cold doesn't care that the system was well designed. It just keeps looking for the one gap. And tonight a human being closes it by hand. 4 a.m. Endurance. Why there are always two. The coldest, longest hour. And now the human factor, which is really the heart of every night like this one. There is always a second person in the cab. Not for muscle. The machine does the pulling. For attention. Here's the truth about exhaustion that makes this rule non-negotiable. A tired mind doesn't feel itself failing. It fails in silence. A person who has been awake for over 12 hours can miss a signal, misjudge a distance, or simply go blank for a few seconds without ever noticing the lapse. On a highway, that lapse might mean a swerve. On a train that needs 2 kilometers to stop, in a place where the nearest help might be hours away over a road that no longer exists in winter, a missed signal isn't a mistake. It can be a fatal one. So there are two. They call signals out loud to each other. They cross-check. One watches while the other reads the gauges, and then they trade. Redundancy up here is not a luxury, and it is not about strength. It's the same principle as the fail-safe brakes. Never trust a single point that can quietly fail. The frost does not care whether you are tired. So the system puts a second set of eyes in the cab, precisely because the first set cannot be trusted to notice the moment it stops seeing. And there's the isolation to sit with. This line runs hundreds of kilometers, much of it cut off from any road all winter. If the train stops out here, really stops, there is no pulling over and waiting for someone to arrive in 20 minutes. The two men in that cab are, for long stretches, the only human beings for a very long way in any direction. The warmth in that cabin is the only warmth. That's a particular kind of alone that most of us will never know. 7 a.m., arrival. The Mashish never slept. The sky doesn't so much brighten as turn a shade less black. The train rolls into the yard. 3,000 tons that left in the dark arrive in the dark, and the man who watched the track all night finally stands up. He will hand the locomotive over, and it will not be switched off. It will keep idling, breathing its low winter rumble, waiting for the next crew, because down here a running engine is a living engine, and nobody dares to let it die. The airlines will be checked again for ice. The rails he crossed will be walked and inspected. The whole quiet machinery of the far north resets for another night exactly like this one. The frost does not care whether you are tired. The engine does not care whether it's Christmas. The rails do not care that a man has been awake for 14 hours watching them. Out here, the machines and the people who run them share exactly one job. Keep going, no matter what the temperature says. Everything is built backwards from how you'd expect. You brake by letting go. You keep the engine alive by never turning it off. You trust the driver least of all, and build the safety into the physics. It looks strange from the outside. From the inside, at -45, it's the only way anything survives the night. And most of us will never see any of it. But nearly every product on the shelves near you, at some point in its life, moved through a frozen night exactly like this one, on a thin film of steel, watched over by two tired people and a machine that was never allowed to sleep. If you made it all the way to sunrise with them, hit that like button. It tells me you want more of these hidden engineering nights, and I'm already working on the next one. And tell me down in the comments, could you do it? One full night in that cab, at -45, staying sharp until dawn, I read every reply.